Welcome to the course on game theory in the autumn term 2020 at the University Mannheim. This is the fourth video of week 9. Now we come to section 5.4 on repeated games. A repeated game is a finitely or infinitely often repeated game in normal form. So it can be modeled as an extensive game without chance moves and without perfect information. One has a special case was given in example 5.8.4. You remember that, so the point is that in each period a game in normal form is carried out, and there the players have to choose simultaneously their strategies. Therefore, at that moment, one player does not know the simultaneous choices of the other players. Therefore, the information is not perfect. So one can model this as an extensive game without perfect information by pretending that the players act one after the other, or choose their strategies one after the other, but that one does not know the choice of the others. This then gives non-trivial information sets. So, Nash equilibria of such games had not been defined in section 5.3, but they are trivial, and they are just the Nash equilibria of the associated games in normal form, and they had been defined in section 5.3. But the notion of subgames and subgame perfect equilibria will also be needed, and that needs more care. It was not given in section 5.3, so below we will give it for the special case of repeated games. So before starting seriously with the definitions, I will already give some overview. There's a big difference between finitely repeated games and infinitely repeated games. Finitely repeated games behave like usual games in normal form. They might have few or no Nash equilibria, or many, depending on the game. And they might also have few or many or no subgame perfect equilibria. On the other hand, infinitely repeated games usually have a vast number of Nash equilibria and subgame perfect equilibria. Usually so many that it's not so obvious why these notions are useful at all. There are just too many of them. You will see it in the next courses here, in the next slides and next videos. So in finitely repeated games, cooperation is possible only if they have very special properties. On the other hand, cooperation is possible in all relevant infinitely repeated games. So in the following, first finitely repeated games will be treated, and then infinitely repeated games. But the next definition presents both of them. Now I'm going to be precise. So we start with the game gamma in normal form, player set script A, space of strategy combinations big S, and utility function big U. So the big letter T here denotes a natural number or infinity, and it will be the number of periods, how often the game will be played. And delta will be some discount rate. Delta will be a real number between strictly bigger than 0 and lesser equal 1 if t is a finite number, and it will be in the open interval from 0 to 1 if t is infinity. So the t times repetition of this game gamma with this count rate 1 minus delta will be defined now, and it is then a game in normal form, which I will denote by gamma of delta t. So gamma is the letter for the original game, but with the arguments now it means something different. Gamma of delta t is now the t times repetition of the original game, with this count rate 1 minus delta. The player set is the same, but now the set of strategy combinations is denoted by a large sigma, and the utility function for this game is now denoted by the letter W. And informally, it is as follows. So the game gamma is repeated t times. The single repetitions are called periods. And after each period, all choices of all players in the past periods are common knowledge, but only afterwards. So within one period, a player does not know the simultaneous choice of the other players. So, but that one knows afterwards everything what had happened before. This is called perfect monitoring. And the utility value W upper I for the player I will be a discounted sum of the utilities of the single periods. And I will give precise definitions and formulas below. So now let's be more formal. Sigma is a product of spaces sigma 1 to sigma m, where sigma I is the set of strategies of the player I. Now I have to say what this strategy is. So a strategy small sigma upper I of the player I is now a tuple of maps of reactions of player I in the small teeth period to everything what had happened before. So sigma I with lower index t is a map from the t-1 fold product of the strategy combinations to the strategy space Si of player I. And the interpretation is as follows. At the period small t, the player I knows all the choices which the players had done in the t-1 periods before. And at each period, the choice of the players together was one strategy combination in big S. So the total history of the game before the small teeth period is t-1 tuple of strategy combinations of the original game. And this is then the input for the map sigma it, and the map sigma it then chooses again a strategy of the original game for the player I. So the player I reacts to the history of the game up to the teeth period by choosing again one strategy of the original game. So in the total strategy of the player I is then the tuple of all these reactions at all possible periods small t. So sigma I is this tuple of these reaction maps sigma it for all the small periods t from 1 to big T. So here the upper index t-1 does denote the t-1's power of the set S. And here I put S in brackets to indicate this. Especially the 0th power of S is by definition just a point. And so the maps from the point to Si is just the set Si itself. So as for extensive games, we have again in 5.2 and 5.3, we have again a map beta, which associates to such a complete strategy combination a result, somehow a final play, or here it is then the tuple of strategy combinations for all periods. So, and the idea of construction is just the same as before, it's inductive. So we start with some complete strategy combination of strategies. Sigma is a tuple sigma 1 to sigma m. And for each player, it is this sigma I is again the tuple sigma it, which I had explained above. So, and to such a complete combination of strategies for all the players of the repeated game, in each single period, one takes the strategy which is prescribed by the history and by the strategy. I should be more precise. So let's look here at this downstairs. So we have again a map beta, and beta of sigma is again a tuple of strategy combinations. So beta t of sigma is in S. So it's a strategy combination of the original game. So and we get this for all small t, and the value for one small t is arises from applying the strategy of the repeated game, sigma it, to the history of the game, the tuple of strategy combinations which one had before. So here on the left-hand side you see beta ti, whereas here is no index. Here we have the whole strategy combinations, but for the earlier periods. So it's just the same idea as always with this map beta, that if one has a complete tuple of strategy combinations, then one knows at each step what each person has to do next, and then the game develops like a machine automatically. So, now the next step is now the utility value. So for some delta in the open interval from 0 to 1, now one takes something which is multiplied by the geometric sum. The utility, one has a discounted sum of the utility values for all periods. So ui of beta t of sigma is the utility value of the tth period of the game. And at the tth period, we have the beta t of sigma, which is a strategy which comes from which is the study of the combination of the old game, of the original game, which comes from the strategy combination sigma of the full repeated game. So in here we have now the weighted sum, a discounted sum with its factors delta of up to t minus 1. And I have a factor here in front of it. And the reason for this factor is that if these values here are all the same, then wi would be exactly this value. So the factor in the front is somehow the inverse of the geometric series, sum of delta up to t minus 1, from 1 to t. So if here this factor, I say it again, would be constant, independent of t, then the whole wi of sigma would be equal to this value, because the value of the geometric sum, delta up to t minus 1, is just the inverse of the factor in front of it. So that's the reason for the choice of these values here. For delta equal 1, it's slightly different. Then we have just the sum, the average value of these utility values, and then we need the factor 1 over t in front. And again, if the utility values for the single periods would be all the same, then the wi would be exactly equal to this utility value, because it's just the average of the utility values which we have for the single periods. And this fits now to the small calculation which you see on downstairs, which everybody knows from analysis 1. If delta goes to infinity to 1, then the quotient on the left-hand side here goes to 1 over t on the right-hand side. So the two formulas are related. For delta going to 1 and finite t, the upper formula tends in the limit to the lower formula. So these are useful and sensible definitions of utility values. Now next, a Nash equilibrium of this repetition is just a Nash equilibrium of the associated game gamma sigma w in normal form. Here in front I promised that we will define sigma and w, and here you see the definition of sigma, and here you see the definition of w. So now we have this associated game in normal form for the repeated game. And the Nash equilibrium of the t times repeated repetition is just a Nash equilibrium of this game itself. But Nash equilibria will not be so nice. It will be better to look at subgame perfect equilibria, and in order to define them we need subgames. So I now will again define a subgame of a t times repeated game, gamma. So of course informally it's quite clear what one has to do. One has to choose one period t prime maybe, or maybe some period delta, and then look at the rest of the game starting from the period delta. And that's what one does, and that's what I make now more precise. So subgame of the t times repetition gamma delta t of a game gamma is now a pair, namely a t prime time repetition of the same game gamma, which you see here, gamma delta t prime. That's the first ingredient of the pair. And then the second ingredient is a delta tuple of strategy combinations. It's written here on the right, lower right side. So A from 1 to delta, is a delta tuple of strategy combinations of the original game. So one has essentially now here a smaller repeated game with a shorter period, t prime, but one has also some additional information. And yeah, by saying what it is. So, and we have a delta, the big delta here, such that t prime is equal to t minus delta. So that means the idea is that one lets delta periods pass, and starting at the period delta plus 1, then one starts this subgame and goes on playing. But one remembers what has happened before. And what has happened before, that is in this tuple of strategy combinations RA, this delta tuple of strategy combinations. So this subgame is isomorphic to the game gamma delta T prime, so without this history. But this extra information, this history, is important for the next statement. So a subgame is not just a shorter repetition of the original game, it's a shorter repetition plus some extra information which gives us a history, what has happened, what has happened before. Namely, a strategy combination sigma of the full T times repetition induces a strategy combination sigma prime for any subgame gamma delta T prime with some history here. In the following way, so to get a strategy combination at some period T, we have to say how this function here is defined, this map is defined, and we have to apply it to some tuple of strategy combinations for the history of this subgame, which are strategy combinations as B from 1 to T minus 1. And we have to define now the resulting strategy of player I. And we do that. Here we look at the, we do it by looking at the full strategy combination of the origin of the big T times repeated game. And there we look at the period delta plus T. And so now we take here as argument the history of the game before the subgame starts, and then we add the local history of the subgame. So this first part here is the old history before the subgame starts, and this here is the local history of the subgame before the period small t. And together then they give the whole history of the full game before the period delta plus t. So to this history we then apply the full strategy, the strategy of player I at the period delta plus t. And the outcome is then the strategy of the subgame at the period t. So that's what I want to say here. Now with this notion of induced strategy combination, now we can go into the notion of subgame perfect equilibria again. So we have now a T times repetition gamma delta T of an original game in normal form gamma, and a subgame perfect equilibrium is now a strategy combination sigma and big sigma of strategies of the repeated game, such that for any subgame the induced combination of strategies is a Nash equilibrium. So this is exactly the old idea of Reinhard Selten for extensive games. And here we have adapted it to the case of repeated games, which are special extensive games without perfect information. So for this case, we didn't have defined subgame perfect equilibrium in section 5.3, therefore I had to do it here. And I wanted to do it anyway because here it is rather something quite explicit and easy to understand. So we will usually make one more assumption which makes life easier, and it's standard. Usually we will assume that for any player I, the set of strategies of the original game, SI, is compact, and that the utility function in the original game from S to R is continuous for the player I. So we have seen this assumption from the first lecture on. They are really standard and they hold most often. And they make life much easier. So I do not demand that SI is connected. So SI might well be a finite set of strategies. So then it is a finite discrete set. This is compact. And in that case, continuity is an empty condition. UI is just any function from this finite set to the real numbers. So continuous is strong only if you have some component, but I don't demand that SI has only one component. It might have many components, especially it might be a big finite set. So, and if these standard assumptions hold, then we get something good, which we already know well. Then we get special strategy combinations which have quite natural properties. Here, this kind is a realization of a minimax strategy, I think, what I have here. So S with square brackets I is a strategy combination such that I think it is a realization of a maximin strategy. So here, player I can assume that he acts last after the other players, and the other players know it. Player I wants to maximize his result, and the other players want to minimize it. And then we come to this inf sub, which you see here on the right hand side. So it's here. So the other players know that player I will choose the best possible strategy after they have chosen S minus I. And they are not friendly to him, they want the worst for him. So they choose S minus I such that this gives the infimum over all these suprema of SIs for the total values. And the whole strategy combination SI and square brackets now is really a realization of this. So the part of the other players is such that the choice of SI afterwards really gives just this inf sub. So here I say that these two values shall be equal. So this is I'm not sure whether it's a realization of maximin strategy, but here the idea is somehow here that player I chooses last, and the others know it, and they want the worst for him, and they choose their strategy that they get the worst for him, and he chooses his strategy afterwards that he gets the best out of the situation. So the resulting value is the value UI min-max. So, and we will use the vector of all these resulting values for the different players later in the infinite repetition of a game. We will not use it for the finite repetition. So now still some remarks on the finite case. If a game in normal form has Nash equilibria, if the original game has Nash equilibria, then any sequence, t times sequence of Nash equilibria is a subgame perfect equilibrium. And the proof is an exercise. And in the case t equal infinity, there are always also other Nash equilibria. I said already that one then has a vast set of Nash equilibria. And for finite t, sometimes, but not so often. And many of these other Nash equilibria, they are related to the notion of cooperation of the players. So Nash equilibria of the t-times repetition, which are not just sequences of Nash equilibria of the single old games, they are related to cooperation of the players. Now this was a general remark for finitely and for infinitely repeated games. The next remark is only for finitely repeated games. So in a finite repetition of a game, a subgame perfect equilibrium must restrict to a Nash equilibrium in the final period. Because in the final period there's nothing more to happen. The subgame in the final period is just the original game. So a Nash equilibrium there is the Nash equilibrium of the original game. So a subgame perfect equilibrium of the whole game must restrict to a Nash equilibrium in the final period. So and if this original game does not have any Nash equilibria, then any finite repetition of it has no subgame perfect equilibria. So and this stands for itself. That's a negative but instructive observation. But it tells us also something for the section 5.3. We have seen that such a finite repetition can be modeled as an extensive game without chance moves and without perfect information. And now from these repeated games we understand that it may happen that such games do not have necessarily subgame perfect equilibria. So here we have extensive games without perfect information, and we see very concretely here that we can easily construct such games which do not have subgame perfect equilibria. So therefore the theorem 514 has no chance to hold for extensive games without perfect information, because here we have counterexamples. Here we have games which do not have any subgame perfect equilibria. Theorem 514 had told that in the case of extensive games with perfect information, backward induction gives us all the subgame perfect equilibria, and especially there exists subgame perfect equilibria. But here, not necessarily anymore. So we can construct finite repetitions of games without Nash equilibria, and then these finite repetitions will have no subgame perfect equilibria. So, and here I want to finish this video. In the next, there come two examples of finite repetitions of games in normal form. In the first one, cooperation will be possible. That's the more complicated one. In the second, not. The second will be very easy. The first one will be more difficult. But here I stop this video. Thank you very much for your attention.